Welcome to Brain Vision.
In this question, we are told that we performed a set of experiments on a one-electron atom and that we have measured the wavelengths of photons emitted from transitions ending in the ground state. And we've been given an energy level diagram. We're also supposed to assume that the ionization energy of this atom was found to be 17.5 eV. So in this question in part A, we are asked to calculate the energy of the atom in each of the levels, n equals 1, n equals 2, etc. So in order to do this, we're going to take advantage of that ionization energy. So I'm just going to write that as EI. And the ionization energy is basically the amount of energy we need to give to the ground state atom in order to liberate the electron from the nucleus of the atom. So this is actually the energy that is associated with the atom in the ground state. So the energy of the atom in the n equals 1 state is just going to be negative 17.5 eV. And then if we give it 17.5 eV worth of energy, then the electron will have the ability to escape the atom. Now, for the rest of the energy levels, what we do is we take that ionization energy and we divide by the energy level squared. So if we're in the second, state, then we're dividing by 4 squared, and that will give us the energy level of that particular state. So this comes from the Bohr model of the atom. So we're just taking that directly from there. So let's go ahead and put this into practice. So the energy of the second state will be 17.5 divided by 4. And that will give us about negative 0.438 eV. And then so on and so forth. So E3 will be negative 17.5 eV over 9. So that will give negative 1.94. And then we've got E4 will be divided by 16. 4 squared is 16. And so we get about 1.09 eV, negative as well. And then E5 will be negative 17.5 eV over 25. So that will give negative 0.7 eV. So these are the answers to part 1. These are the energy levels of each of the states shown in the diagram. Now in part B, we're asked if the electron makes a transition from the n equals 4 state into the n equals 2 state, what wavelength of light would it emit? So basically, the energy change in going from the n equals 4 state to the n equals 2 state will be carried off by an electron. So the first thing that we need to do is calculate what that actual energy change is. So the delta E here is going to be E4 minus E2, right? What is the change going from 4 to 2? So that's negative 1.09 eV minus so plus 4.38 eV. Oh, I suppose actually it would be the other way around because we want final minus initial. There we go. So negative 4.38 eV plus 1.09 eV. And so for that, we get a value of negative 3.29 eV. And as I said previously, the atom is losing this energy, the negative 3.29 eV. So the photon is going to carry away positive 3.29 eV. So we know that the photon's energy is related to its frequency by this formula, as well as its wavelength. So we can go ahead and plug in the 3.29 eV for the energy of the photon, and then we can plug in the Planck's constant, the speed of light, and solve for lambda. Now, we do need to be careful here because our energy at this point should be in joules. So in order to convert from eV to joules, we're going to multiply by 1.6 times 10 to the minus 19. So that gives 5.25 times 10 to the minus 19 eV equals all of this. So lambda is going to be h times the speed of light divided by the energy. So that gives us a wavelength of 3.78 times 10 to the minus 7 meters, or more commonly, we usually write wavelengths as nanometers for light, so 3.78 nanometers, and that is our final answer for B.